All right, so unit two, polynomials. I think the key things I remember are basic equations, because understanding basic equations helps you understand both end behavior and behavior around a zero or a root or an x-intercept. So just providing maybe like four. You got y equals x squared, y equals x cubed. And then x to the fourth. And from here, you can kind of make assumptions / conclusions. What do we notice? That the even powers and behavior is up and up. If I put a negative leading coefficient, the end behavior would be down and down. Odd powers and behavior is kind of diagonal. If I put a negative leading coefficient, things would change. So that's end behavior. And the second thing is your behavior around your zeros. You can see odd powers, because if you take a negative number to an odd power, it stays negative. If you take a positive number to an odd power, it stays positive. It's because of that fact we can see we change signs at the zero, like x equals 0. To the left negatives, we have negatives. To the right negatives. Here, to the left of 0, cubed will be negative. So we see we do change signs. One thing is that the x cubed would have to slow down. If you take a decimal to the third power, it's going to get closer to 0, like 0.1 to the third power. It's 0.1 times 0.1 times 0.1. It would get closer to 0. So that's why it slows down on the way to 0. Versus even powers. Take a number to the even power, it will always be positive, or there won't be a sign change. That root won't change signs. It'll always be the same sign. It will always be positive. So end behavior and zero behavior, just based on that. And that's all you need to know. Some key things. End behavior, when we look at plugging in infinities, we don't care about all of the terms, because it'll be the fastest growing term that will dominate what's going on at the ends when you plug in infinity. So this is a negative x to the 6, so this is going to have end behavior that's down and down. As I approach negative infinity on my x's, my y's would approach negative infinity. As I approach positive infinity on my x's, my y's will approach negative infinity. Make sure you understand that. These are x's, x's, x's. These are y's, 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 y's. So I'm looking for negative and negative for my y's as my x's approach both sides of infinity. Here we start with a positive x cubed. If I flip it, we would go here and here. So as I go to the left towards negative infinity, my y's are going to be going towards positive infinity. If I go right towards positive infinity, my y's are going to be going towards negative infinity. So I'm looking for negative infinity, positive infinity, negative infinity, negative infinity, positive infinity, positive infinity. Okay, I'm given the limit statements that if I go towards negative infinity, I'm going to be down towards negative infinity. If I go towards positive infinity, I'm going to be going that way. So I'm looking for an even degree power with a negative leading coefficient. Be careful, things might be ordered not from biggest to least. I can see these are cubed first, 6, 4, 1, 5, 4, 4, 1. So this negative x to the fourth would have that end behavior. Total of the end behavior is going to look like, what could be a and n. If I'm going towards negative infinity, I'm up towards positive infinity with my y's. If my x's are going towards positive infinity, I'm going to be going up towards positive infinity as well. So I'm looking for a positive x to an even power. So positive x to the even power. Not worrying about this or this. When we're plugging in infinities, adding those things will be like adding small decimals to large numbers. We don't care about them. All right, now we are given the graph. We can see the end behavior. We can see it's going to be some sort of x to the even with a positive leading coefficient. We can see we have 1 0, 2 zeros. This brings us to the next thing that we have to remember is if we have x to a power plus other stuff, there's going to be p solutions or p roots. That could be a combination of real and then pairs of complex. Remember, if you ever are solving an equation like this, that if you have a complex root, they come in pairs. So we're always looking for multiples of 2 of complex roots, and then the amount and the multiplicity of our other roots. Here I can see there's going to be some x minus a number to probably the third power. This will be x plus a number. That way when I plug in a negative x, I get that, and that's to the first power. So I'm looking for a cubed and a first. I can see multiplying them all out, I get an x to an even. I get x minus a number cubed. So there's that x minus 2 cubed. If I plug in 2, I get 0. We will slow down around that because of the third power. And then here, x plus 3 means negative 3 would be the root. And that works out well. What could help us understand the shape of polynomials is doing a sign analysis. Now, where do signs change? Signs change at potential vertical asymptotes or zeros. So zeros of polynomials, either in fraction form or just in general, are important. So what we can do is list off these zeros. These are the values that make this 0. And then do some sign analysis. Now, the sign analysis can be done 2 different ways. You can either use test points, knowing that signs will not change in between zeros, or you'd have another 0. Or use one test point, or use end behavior, and then look at the multiplicities of your 0, knowing whether or not you change signs at the 0. So I'm going to do that. That's the way I like to do things. I'm going to plug in one test point all the way to the end of things. And I see I'll get a negative, a positive, and a positive. Okay, 5 times negative 2 is negative, 5 minus 4 is positive, 5 plus 1 is positive. So I know I got a negative number. Now I can see, because it's x minus 4 to the first power, that this factor would change signs. So you could see this as well if you use a test point. This first factor would stay negative because it's 0 to 0. The second factor, however, changes its sign to negative. This factor stays as positive because it'll change signs at -1. And we can see, yeah, we do change signs at 4. There's that first power showing you will change signs. Now you would see at here, if you plug in like -0.5, this factor would change. This would stay positive. This would also stay positive. Nope, this would be negative. What did I do wrong? Sorry. This would stay positive. This would stay negative. This would stay positive, or we would just change signs there. Here, this would be positive. This would remain negative. And now this factor would change to be a negative to make that positive. It's probably just easier, because even I was like messing up on it because I was looking up here, to say this is negative, change signs, because of the multiplicities. Be careful, make sure you see whether it's less than or equal to. This is just less than. What are values that are less than 0? Negative values are what we're looking for. Here are my negative values, here are my negative values. So between -1 and 0, and then after 4. Okay, same deal. Let's do this a little bit quicker. I got -3 makes this 0. I got 0 makes this 0. I got 4 makes this 0. Test 1 test point, like 5. Order of operations, square the values first, then make them negative. We'd have a negative, positive, positive. Here's another thing you could do. This would be an x negative x to the 1, 2, 3, 4, which means your end behavior would be down and down. That's another way to determine that this is negative. At 4, the degree is 1. We will change signs of that factor. At 0, we see the square. We will not change signs at 0 because this factor won't change signs. And then at negative 3, because the multiplicity is 1, we will change signs. Greater than or equal to 0, that's positive values as well as 0. Here are my zeros. Here are my positives, so I want to include the zeros and all the positives. I'm looking between and including negative 3 and 4. When is f bigger than g? Good question. Probably what I would do is subtract g from both sides and determine when f minus g is bigger than 0. So what's f minus g? Well, first of all, make sure you're subtracting all of g. And when you subtract all of g, you realize this is a negative, positive, positive. You get negative x squared minus 2x plus 24. You could factor this as you see it. It'd have to be a negative x plus a number times a x plus a number. But it gets a little bit complicated because one of those x's is negative and one is positive. So what I like to do is pull out a negative 1, flip the signs of all of these terms, and we factor a quadratic. Now, we know that x plus a number times x plus a number equals x squared plus 2x minus 24. Our goal is to find the two numbers, understanding the distribution of this. X squared, x times this times x. You would add those two amount of x's together, and then this times this would give us our numerical term at the end. So we're looking for two numbers that add to get 2 and multiply to get negative 24. That's positive 6 and negative 4. Don't forget about this negative 1. We again have our zeros. We understand it's a negative x squared, or we do a test point. We plug in something like 5, positive, positive, negative. We will change signs because the multiplicity is 1. This factor would change. We will change signs because the multiplicity is 1. When are we bigger than 0? We are going to be bigger than 0 at our positives. Our positive values are bigger than 0. Here are my positive values between negative 6 and 4. Well, what are our zeros? Well, we see we have a root at 3, but what's going on here? Well, we're going to have to somehow solve this. I'm going to try to factor it again. If I can't factor, my backup is always the quadratic formula. Are there two numbers that add to get negative 6 and multiply to get positive 9? And there are. It's x minus 3 and x minus 3. So this actually turns into x minus 3 squared, which means g of x turns into x minus 3 cubed, which means I have one distinct real solution. I know there's going to be 3 solutions total. There it is. X equals 3, whose multiplicity is 3. It's got one distinct real zero, no non-real zeros. We're starting to think there could be a complex zero, but there isn't here. Understanding polynomials, you will be able to determine the type of polynomial by which rates of change are constant. If this rate of change was constant, then I know I have a quadratic, a linear. It's not. So I find the rates of change of my rates of change, and I realize that these rates of change, if they were constant, would show that I'd be quadratic. The second rates of change being constant, I have a quadratic. Here, the third rates of change show that this is a cubic. This is a question that you would probably want to try to do with a calculator, but we're not letting you. You have to be prepared to look at rates of change of rates of change. Cool. And then what could be asked of you is like, what's this next value here? Well, just like kind of back yourself up. This has to be +1, which means this has to be +3, which means this has to be +4, which means this has to be 3. Okay, cool. That's unit 2.